Hello and welcome back to this low-level JavaScript series all about building a 16-bit virtual machine from scratch. In this episode, we're going to finish off the work we started on the move literal to register parser and explore how we can perform further transformations on the structured data that we pass out of the assembly language. At the end of the last episode, we built a simple state machine capable of parsing the structural part of a square bracket expression, but we hadn't tackled the similar but slightly more complex bracketed sub-expression parser. The reason for the extra complexity is that the bracketed expressions themselves can contain bracketed expressions, meaning that we're dealing with a recursive structure. We're going to have to attack this problem with a state machine with more states and more transitions, and we'll be making use of a stack. Anytime you have something recursive in computer science, there's usually a stack data structure hiding around the corner. Now, we've covered stacks on this series already in the form of the machinery that handles subroutine calls. Whereas the stack there was keeping track of the state between different levels of function calls, the stack here is going to be keeping track of different levels of bracketed expressions. So let's dive right in. We're trying to parse an instruction in this form, and specifically this part of the instruction. In order to cover the most complex case, let's make this expression a little bit more nested, which gives us a bracketed expression with an extra level of nesting, as well as a single expression containing 2 operations and 3 operands. This is the state machine we're going to use to process the expression. As a side note here, it actually has less states than the state machine that I showed at the end of the previous episode, and that's because after making the video, I realized that I had massively over-engineered it, and some of the states were redundant. But that's actually one of the really great things about framing your problem as a state machine. It can help you realize and pare down to what the essential parts of the problem really are. Okay, so in addition to the state transitions themselves, just like before, we're going to have an expr array to store the results of this expression. This time, however, we're also going to have a stack, and that's going to hold a reference to the expr array. When we start out, we're in the descriptively named element or opening bracket state. In this state, just like in the expect element state from the last episode, we're trying to pass either a hex literal, a variable, or another bracketed expression. Here we find a hex literal, so we can push that result into the array at the top of the stack, which in this case is just the expr array, and move to the operator or closing bracket state. In the operator or closing bracket state, we might find an operator, but we of course might find a closing bracket, and anything else would be an error. Here we capture the operator, we push it into the results, and we move back to the element or opening bracket state. When we peek at the next character, we see that it's an open bracket, so we move into the open bracket state. The job of the open bracket state is to consume the bracket character and to set up the stack for the next level of nesting. We can achieve this by pushing a new array into expr and then pushing a reference to that array onto the stack. Then we can transition back to the element or opening bracket state again. Here we find a hex literal, we push it to the array at the top of the stack, but this time that array is actually the nested array inside expr. After transitioning to operator or closing bracket, we capture a plus symbol and move again to element or opening bracket. We find a variable, we move straight back to the operator or closing bracket, and now instead of finding another operator, we find a closing bracket. The job of the close bracket state is to unwind the stack by one level. It pops the reference at the top of the stack, checks to see if the stack is now empty, and if it is, we've reached the end state. In this case, there's still a reference at the top of the stack, so we're not actually done yet. We transition to the operator or closing bracket state again, capturing a minus and pushing into the array at the top of the stack. That array is of course just the expr array again, so the operator ends up there. Next, we move to the element or opening bracket state, where we capture a hex literal and back again, finding our final closing bracket. After we pop that reference from the stack, it's now empty, signaling that we're complete, and the final expression result array looks like this. In order to put this into code, we're going to write another coroutine parser and create another object representing all the different states. We'll start out in the element or opening bracket state and set up the expr array and the stack. And before we do anything with the state machine, we need to consume a bracket character, because whatever parser we came from won't have done that. Then we can set up our infinite while loop. We peek at the next character before checking any states, since more than one state will want to know what the next character is. Then what I like to do sometimes with a state machine is to just write out all the blocks for all the states, so we can just move through the implementations without forgetting any, and making the program panic at the end if we get into a state that we didn't expect. For the first state in the list, open bracket, we're going to have to consume an opening bracket, push a new array into expr, and push a reference to that new array into the stack using this last function. Last is a super simple function that we're going to use a couple of times, and all it does is return the last element in an array. We can go back to the open bracket state, consume any white space that might be around, and move into the element or opening bracket state. The next state in our implementation checklist is close bracket. So after consuming a closing bracket character, we can pop the reference off the top of the stack and throw it away. If there are 0 items left on the stack, then we're actually done parsing this expression, and we can just break out of the infinite while loop. Otherwise, we'll take care of the white space and we'll set the next state to operator or closing bracket. In our element or opening bracket state, funnily enough, the first thing we want to check is if the next character is a closing bracket. If it is, we can actually fail with a more helpful message to the programmer. If not, we can check if we're getting an opening bracket and set the state accordingly. Otherwise, we must be getting a hex literal or a variable, and we can just push that result into the array at the top of the stack, consume any white space, and set the next state. And finally, in operator or closing bracket, we're expecting either an operator or a closing bracket. If the next character is a closing bracket, then we'll set the state and use continue to jump to the top of the while loop. Otherwise, we should only be looking for an operator, which we can of course push into the array on the stack, consume any white space, and set the next state to element or opening bracket. So we've taken care of all the states, and we've made sure that there's a valid route out of the infinite while loop. So all that's left to do with this parser is to return all the results that we've collected. Just like everything else, we're going to need to wrap this up in a nice descriptive type. We can write a function called typify bracketed expression to do this, and add its implementation above. Essentially, it's a recursive function that's going to descend through the expression that we've generated. We can create a specialized typing function for bracketed expression and return that type, wrapping a mapping operation of the whole expression array. For every element in the expression, if it's an array, which of course represents a level of nesting, then we will return a recursive call to typify bracketed expression. Otherwise, we'll just return the element itself. Let's go ahead and see if the move literal to register parser can now handle the more complex form. I'll scroll down here and modify this hex literal 42 to instead be a square bracket with multiple operators and operands and a nested bracketed expression as well. Running this in the terminal gives us a result where we have an instruction, which is a move literal to register with 2 arguments, the first of which is a square bracket expression with a hex literal 42 plus the LOC variable minus a bracketed expression consisting of hex literal 5 multiplied by another bracketed expression with hex literal 31 plus the var variable minus hex literal 7. This doesn't exactly roll off the tongue, but this representation is going to be very easy for the assembler to understand. Now, while studying the output of these expressions, you may have noticed a potential problem here. Both square bracket expressions and bracketed expressions are potentially ambiguous because they don't always take the form A operation B. Instead, they can be, and often are, A operation B, operation C, operation D. We could say that all of these operations just execute from left to right, like this, which would turn our ambiguous expression into a single binary expression. But if we were to replace these abstract operations with real ones, then we'll know from the years of math education at school that B times C should actually be evaluated first, and that our system needs to be able to recognize that. To solve this, we can write a transformation function that will accept either a square bracket or a bracketed expression, and give back a single binary operation, prioritizing some operations above others. We're going to transform both kinds of expression into a single type that we'll call binary expression. Then we can write the disambiguate order of operations function, which will take an expression as its argument. First things first, we can check to see if we're dealing with a square bracket expression or a bracketed expression. And if we're not dealing with either of those, we'll just return the expression as it is. We'll see why we do this a little bit later. Next, we can check if the expression's value, the array that holds the elements and operations of the expression, is length 1. If it is, then there's only one thing inside this array, and that means it's already disambiguated. We can return that immediately. With the simple cases out of the way, now we need to start the actual disambiguation. We're going to be assigning each possible expression a priority based on the operation. An object that maps operation names to priority levels will allow us to easily adapt the code as we add new operations. We're going to search through all the possible operations in the expression and decide if it's a candidate to be disambiguated, based on its priority. In order to keep track of the candidates, we'll create an object with a priority initially set to -infinity. And we can use a for loop to iterate through the expression, starting at index 1 and increasing I by 2 each iteration. This way I is always pointing to an operator inside the expression. We can get the priority level based on the type of the operator and decide if it's a better candidate than what we have now. If it is, then we can set the candidate expression to an object with the new priority level, as well as giving it a key for A, which will hold the index of the left-hand side operand, and B, that will hold the index of the right-hand side operand. Finally, we can store the operation as well on a key called op. With our candidate selected, we can create a new expression wrapped up for convenience in a bracketed expression type, and slice everything until we get to the first disambiguated element. Then we're going to place our binary operation, extracting the actual elements from the original expression array using the indexes. Both A and B are going to be wrapped in a call to disambiguate order of operations, because you need to remember that A or B could themselves be a bracketed expression which is nested. The binary operation will also contain the op that we got from the candidate. Finally, we can slice out the rest of the expression after our candidate. In the end, we return another recursive call to disambiguate order of operations, which will, over the course of a few iterations, reduce our expression down to a single binary expression. Let's scroll down to the square bracket expression parser and map its result using the disambiguate order of operations function. Running this code in the terminal again, we see that we still have a move literal to register instruction, but now the square bracket expression has become a binary expression with a well-defined A, B, and operation. And if you trace it all the way through, you'll find that it has properly grouped up the ambiguous operations. Now, don't worry if this didn't all sink in immediately. With recursive code like this, it's a good idea to fire up the debugger and step through the layers, seeing how the algorithm zeroes in on the final output. And so, after 2 episodes of working on this assembly language parser, we can properly handle one instruction. But luckily for us, this instruction has laid a lot of the groundwork that will make handling subsequent instructions much more straightforward. Thank you to all the low-level JavaScript patrons. Your continued support helps get these videos made. If you'd like to support this channel, you can head over to patreon.com/lowleveljavascript and become a patron yourself, or even just subscribe and share the channel with a friend or a coworker. Thanks for watching, and I'll see you next time.